So now let's look at the next variable that affects where equilibrium lies, which is this idea of pressure. Now I'm going to give you the cheap and dirty first, and then we're going to kind of break into that a little bit further. We're going to go a little deeper. So the cheap and dirty is as follows. An increase in pressure favors the side with the least amount of moles of gas. So what does this mean? Well, when I look at this chemical equation, what I notice is on the left-hand side, I have a total of 2 moles of gas, right? I have 1 mole of A and 1 mole of B. But on the right-hand side, I only see 1 mole of gas, right? So in this case, what it says is that if we increase the pressure inside of the container, we're going to favor the side with the least number of moles of gas, or in this case, and only this case, right? We're going to produce more products. Well, the converse, therefore, must be true. If we decrease the pressure, then a decrease in pressure will favor the side with the greater number of moles of gas. So if we decrease the pressure, what's going to happen is that we're actually going to favor, in this case, my reactant. So we're going to be making those guys over there all the way on the left-hand side. The question really becomes, well, why is that? What's actually happening? And what I am going to toss in there and really alter this cheap and dirty is I'm going to say that changes in quote-unquote pressure are actually changes in concentration, which means that we're back to our Q and K description. Let's take a look and see what we mean. For this one, we're going to do the same exact thing, K equals 1. But this time what I'm going to say is for each of these, I'm going to say that we have 1 mole of a gas. So let's say that at equilibrium. So at equilibrium, we have 1 mole of the gas in a 1 liter container. So put that into perspective. What we're going to be doing is that we're not going to be altering the amount of gases. What I'm going to do instead is I am going to expand or contract the container. And my guess is, as we learned in our gas laws, when I alter the volume of the container, I will therefore then alter the pressure that the gases exert within the container. So let's start off and let's look at this and let's just rewrite this. Instead of as concentrations, I'm going to say I have 1 mole of C over 1 liter, and this is going to be up here at the top, and this is going to be over 1 mole of A over 1 liter times 1 mole of B for every 1 liter. Okay, so it's the same, exactly what we have right above in the purple. Concentration of C over concentration of A times B, right? But now I'm just rewriting it as moles per liter. And so here's what I'm going to do. Let's look at it and let's answer the question we started off with. An increase in pressure favors the side with the least number of moles of gas. In this case, when I increase the pressure, what I'm going to do is I'm going to have to cut the volume. I'm going to have to actually shrink the size of the container. So here's what I want to do. Instead of all of this being in 1 liter, we're now going to make it so that when we compress the container, it's now going to be in something half of a liter. Okay? So instead of 1 liter, all of these are now going to become 0.5s. 0.5 liter and 0.5 liter and 0.5 liter. So if I cut the volume in half, well, that means that my concentration is going to double because 1 over 0.5, that means that I now have 2 over 2 times 2. Okay, well, this 2 is going to cancel with this 2, so that means my new ratio is 1/2. Wait a second. Is this 1/2 the same thing that I had over here when Q, in fact, is supposed to be equal to 1? And the answer is, of course not. So what does this 1/2 represent? Well, as you can already imagine, that 1/2 is once again my value of Q. So if Q is 1/2 and K is 1, that means Q is less than K. And if Q is less than K, Pac-Man has to chomp to the right. Or if Q is less than K, that means that this reaction is going to shift to the right to compensate. So notice, what was the cheap and dirty? An increase in pressure favored the side with the least number of moles of gas. Great. Which was the side with the least number of moles of gas in this case? And in this case, that side would be the products. Now, if you're not sure, if we were to flip this equation around and now I had C on the left, then when I increase the pressure, you know what's going to happen? We're actually going to favor the formation of the reactants. To kind of see how that would work, what I'm going to do now is let's tweak this up a little bit. And now, instead of cutting the volume in half, right, what happens if we double the size of the volume? Well, let's see. So if I double the size of the volume, I'm expecting the pressure to drop. A decrease in pressure favors the side with the greater number of moles of gas. Well, in this case, the side with the greater number of moles of gas is going to be the reactants, A and B. But why? Why is that happening? How exactly does that occur? Well, let's do the same trick again. This time, instead of having 1 mole of C in 1 liter, let's put it in a 2-liter container. And the same thing with A, and the same thing with B. And so that means that I'm now left with, in essence, what's going to look like 1/2 over 1/2 times 1/2. Well, as before, again, I see some cancellation. This 1/2 is going to cancel out with that 1/2. And that is going to leave me with 1 over 1/2, which is the same thing as saying 2. But what on earth is this 2? I thought that we were looking for an equilibrium constant of 1, that's what my equilibrium constant was meant to be based off what we said. And sure, that's still true. So this 2 must in fact be my new value of Q. So in this case, Q is 2. That is greater than 1. Which way does Pac-Man have to go? Pac-Man is going to chomp to the left towards the reactants. Why? Because in this case, the reactants had more stuff. And the cheap and dirty is a decrease in pressure favors the side with a greater number of moles of gas. So, okay, what if you had the same number of moles of gas on both sides? Then guess what? Changes in volume or changes in pressure would have no effect, right? It would have no effect because as you change the volumes, all the ratios are going to be the same. You're basically doing the same shift across the board. If there's no changes in concentrations, then there's no changes in quote unquote the activities, and so therefore everything is going to stay the same. Now, one last little caveat with this. I have often seen on exams and questions where it'll be something like, so let's say we have A plus B producing C, and to the following system at equilibrium, we add an inert gas. So let's say that I added some, I don't know, neon into the mix. It is going to have 0 effect on this reaction, right? Does adding neon alter this reaction in any way? And some of you might be looking at this and going, well, yes, because you add more neon, the total pressure goes up. And it does. But is pressure really what causes this reaction to shift either to the left or to the right? And the answer is no. It's not really pressure. It's changes in concentration. It's altering the value of Q. So if you don't alter the value of Q, then adding an inert gas, adding a noble gas to the mix, shouldn't have any effect on this. It won't alter how this reaction plays out. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.